Hi, and welcome everyone. My name is Francesco Fiusco. I recently joined the ENCCS project. I have a background in fluid mechanics from KTH, where I got my PhD. And yeah, moving on to the interesting stuff. I will try to give you some kind of overview on how we can use Julia for GPU programming and also, well, not so much machine learning, but I will mention some of the packages that we can use for that. And this might be a topic for some other workshop down the line. I hope you can see my screen. So I will start with a short introduction, first of all, to GPUs, just so that we're all on the same page with nomenclature mainly. And then I will move on to some of the features that are peculiar to the Julia language and how they can be used for writing high performance software. So Julia, yes, it's a free and open source language, and it aims to solve the two language problem, and I will tell you all about it in a few minutes. ENCCS actually has some material for Julia programming, particular performance data analytics and performance scientific computing. And as Tur mentioned, this will be featured in our workshop in a few weeks. So just so that we're on the same page about what a GPU is and what are the names of the things that we find inside. GPUs are high throughput accelerators, and they're separate from the main processor. So they have their own memory and their own circuitry inside. Originally, as the name says, graphical processing units were initially developed to support the highly parallel computations that are needed for graphics processing, since each pixel can be treated independently from the others. But as you all know, nowadays they're all the rage to accelerate any workload that is intensive in terms of floating point computation, and the more local in memory, the better. And this is why, this is because compared to a CPU that we see on the left, most of the die size on a GPU is composed of this ALU, arithmetical logical units. So most of the circuitry in a GPU is wired to do computation. There is much less in terms of control units. So there is a lot less room for out of order execution or logical manipulations to the instruction. It's all about heavy math crunching. So data has to be moved manually from the host memory. With host, we refer to the CPU, or the CPU, to the device memory, where device in this case is the GPU. And this is one of the main performance bottlenecks, because most of the times this communication has to happen through this PCI Express bus. And yeah, this had latency to code execution. So we have to make sure that whatever workload we want to run on the GPU, the arithmetic intensity or the heaviness of the computation kind of shadows the latency due to data movement back and forth, even though there are strategies to mitigate that. So this image is uses some of the NVIDIA lingo. So each one of these boxes is a core and can run a thread. GPU thread tends to be much more lightweight than a CPU thread, so it costs a lot less for context switching. And each GPU core, or all the GPU cores, are grouped in groups called streaming multiprocessors. which instead in AMD GPUs are called compute units. But what they are is the same. So there is a number of computation cores supported by a control unit and a local memory that in NVIDIA language is called shared memory, that each thread in a compute unit can access. And then, of course, there is the larger part of the memory that is the video RAM, and that's where the user mainly copies things back and forth through this PCI Express bus. So it is costly even within the GPU to read data back and forth from the video RAM, but the L1 caches and these shared memories, those are very fast. So we will see how we can exploit this to improve performance in our programs. But this is the general idea. So a GPU is made for number crunching. So most of the resources are devoted to floating point units, and there is very little in terms of execution control. So now that hopefully we're on the same page about what the names are, we can move on to Julia itself as a language. So why was Julia born? Well, the idea is that whenever code is run in any programming language, the source code that a developer writes has to be translated into machine instructions to be able to be executed. And there are mainly two ways that correspond to families of languages in which this can be done. So there are interpreted languages like Python and R that translate instructions line by line. So the code written in these languages is interpreted on the fly whenever the script is executed. And then there are compile languages like C or C++ and Fortran that instead have to be translated beforehand, before the program is executed. And there is a software, there is a compiler that does that. And then the program can just be executed. There are also some languages in kind of that mix up this, such as Java, that compiles to intermediate representation, not exactly machine code, but not pure source code, that makes interpretation quicker. But this is sort of the general idea. And well, they both come with pros and cons. So interpreted languages usually are much easier to read and write because we don't need to tell the code beforehand, for example, what type of variable is going to be or the size of an array. So they're much quicker to write, but this, of course, comes with an overhead that is due to the on-the-fly translation to machine instructions. So usually compiled languages can perform faster by orders of magnitude because the compiler, knowing beforehand what the code is going to contain, can optimize it in all sorts of ways. So it happens quite often that in prototyping, a high-level interpreted languages is used, and then when the algorithm is actually proved and it needs to run faster, then it is rewritten in a compiled language for performance. And this is what is known as the two-language problem. So you can't get the best of both worlds. And this is where Julia comes in, because it tries to solve this. So it is an interpreted language, or looks like an interpreted language, and in a lot of ways it behaves like one. The cool trick that happens here is that before each function is executed, Julia compiles it on the fly. And this is what is called a just-in-time compilation, JIT. So you get all the flexibility of an interpreted language, but you can also get the execution speed of a compiled language. The cost, of course, is offloaded to the first execution of a function, because that's when the just-in-time compilation takes place. But then any subsequent execution will be much quicker. And Julia is a language that was designed for scientific computing mainly. So in the words of its developers, we want the speed of C with the dynamism of Rabi. And well, there's a bunch of other implications on design language, like having macros that we will talk about in a second, kind of tuned to scientific computing, so MATLAB-like syntax. But the idea is that, yes, as expressive as interpreted languages, but as fast as C. And they kind of achieved that. So in some of the micro benchmarks that are being run with Julia compared to other languages, if we choose C as the baseline here at 10 equals 0, so this is our baseline, Julia holds its own in most of these benchmarks, and in some cases is even faster. So we can actually get the best of both worlds. And yes, so this is why we're talking about Julia today. So I will just give a short recap of the main syntax, how it looks, and what are some of the peculiar features of Julia language. So we have scalar data types. This is a floating point. Let's execute this code cell. We're defining a float 64 number here containing pi. We have integers. We have Boolean values. And in this case, we have a complex number. And then, of course, strings. So Julia has some kind of typing system with a type hierarchy. And I will tell you about it in a second. But the idea is kind of like Python. Julia is strongly typed. So each variable has a type that may or may be known at compile time. But yes, it is strongly typed. Then we have vectors and arrays that are first-class citizens. So they're defined kind of like lists. And we have array comprehension as well, kind of like in Python. Matrices are a subtype of arrays. So it's a matrix is just a bidimensional array, whereas arrays themselves can be of any dimensionality. So in this case, we're having a 4-dimensional tensor. And if you're used to MATLAB or even NumPy, there is broadcasting of operators. So broadcasting in this case means more MATLAB style. So adding a dot to, let's execute this, adding a dot to whatever operator leads to it being used element-wise on each element of an array. So in this case, B1 is the squared of each element of A1, and B2 is A2 minus A1, where the minus operations perform element by element. And this can be used, for example, also in assignments. So we can do element-wise assignment. And yes, so it gives us a very nice way to do element-wise operations. We can also have composite data types, such as what would be called a struct in C. And for example, in this case, we have the point structure. And this can be parametric. So if you're familiar with templating in C++, this is kind of the Julia equivalent. So we're defining a structure where X and Y are of the same type T, but this type T is not known beforehand. So you can have, for example, a point where these two are integers, or a point where they're floating numbers. In this case, we're restricting the T type to be a subtype of real. So this means that basically can be any real number. And so we will have different instances of this point structure depending of the T that we choose when we actually instantiate one of these objects. And this allows for very nice performance optimization that we can see in a second. Of course, we have our basic flow control flow code execution control. So we have for loops. We can also loop over any iterable or any collection using the each index function. So it's kind of like a for each loop in other languages. We have key value data types called dictionaries, like Python dictionaries. And we have our usual if-else blocks. So as you can see, the syntax is quite similar to MATLAB. And this was a conscious design choice to have a kind of familiar environment for people who are used to scientific computing. And then we also have while loops. It's also very easy to work with files. There are, of course, higher level libraries to open, for example, CSV files or other types, but very basically, this is not too different from Python or C for that matter. So we open a myfile.txt in write mode. This, for those of you who are familiar with Python, is kind of like a context manager. So the doF is kind of like writing with open in Python. So this yields our variable here that contains a reference to the file. And then we can do the same thing, reading it in opening it in read mode. So we yield the same pointer to the file, and we read all the lines that we have just written. So this kind of do and syntax is quite similar to a context manager in Python. We have functions that are first-class citizens in Julia. So Julia has deep roots in functional programming, and it really shows. So in this case, this is just a summing function. By default, the last expression that in the body of a function is the return value. So we don't need to explicitly write return here, but it's not a problem if we do. We have keyword arguments that are added after a semicolon. So in this case, we have no position arguments, only keyword arguments. And yep, it's quite straightforward what happens here. So pass go fetch as a greeting and dog name as Fido. We also have optional arguments. So we can prescribe default values. It's quite similar to most other interpreted languages. One thing that is interesting is that in a true high-level fashion, we haven't prescribed the type of the argument so far. And one cool thing is that we can get really fast code without actually being forced to do it. So earlier above, we declared this function fxy. And now we called it with the arguments 3 and 5. So what Julia did behind the curtains was checking the type of these two variables, they're both ints. And he created a specific version of the function f that is compiled with integers as inputs. So the first time we execute it will be a bit slow, or in this case, it was very simple, so it wasn't that slow, but it's a bit slower. But then any subsequent calling will have a compiled function that takes integers as inputs. If we had called it, for example, with 2 floating points, we would have done the same thing, but writing an f that with 2 floating points. In this case, we're doing it explicitly, but there's no really further optimization done if we prescribe these two types explicitly, because the first time that Julia finds it with a type that he hasn't seen before, it will just compile it on the fly. We can also specify return types. And again, unless we're dealing with some specific types that we created, for example. So we have to tell the compiler how this function is going to work. The just-in-time compilation will do just fine, and we get very performant code without actually having to deal with lower level optimization ourselves. So moving on to some even more special features. As I said, there is a hierarchy of types, and this is what we wrote, for example, up here when we created our structure type. So we restricted the T type to be somewhere under real. What does this mean? It means that there is a tree. For example, this is all types of numbers you can have in Julia. So we have a type called number, and they can be either real or complex. And a real number can be a rational or integer or fixed point or some kind of floating point number. Integers can be signed or unsigned, and so on. So we have specific types, but there is a structure in here. And this is very interesting because given this hierarchy of types, this is what the compiler uses to be able to optimize the code as efficiently as it does. Because if we restrict, for example, variable to be under real, then specific functions can be created for all the types that are under here. There are two types of types. There are abstract types that are just used as nodes in this hierarchical structure. And there is a system of informal interfaces that these types have to obey. For example, an array has to provide a series of functions such as getting the index, moving back and forth in the array, and exposing the size. This is not strictly enforced. It's not like in the C++ sense or in the Java sense that something that inherits an interface has to implement it wholly. But it's more informal. At the moment, at least, there is talk of extending it. And then there are concrete types that are actually the types that we can instantiate for variables. For example, an array normally descends for the abstract array as a supertype, but it can be of any type, such as dense array, sparse array, who array will be a GPU array. So as long as it inherits from abstract array, the compiler will know that it's an array. This is the same thing, for example, for floating point numbers. We can have different precision, but they all inherit or descend from abstract float. And this structure is very important for the optimization that happens when the code is executed. As I mentioned before, functions are first-class citizens, so they're actual objects that can be manipulated. This is where it gets slightly more tricky if some of you come from object-oriented programming background. So a method in Julia is not a method of an object like it would be in Python, Java, or C++. A method is a specific version of a function. So let me explain this better. We have this function sum square that returns the sum of the squares of two numbers that we pass to it. And this is kind of like the template of a function. So we give it two objects and it will do this operation on these two objects. But how this will actually happen depends on the type of variable that we pass to it. So for example, we have the version where we pass two floats, and in this case, it will not make a lot of difference. We have the version where we pass it to integers and the version where we pass it to complex numbers. So in this case, if we do all this, now we have the sum square is a generic function with 4 methods. This means that the Julia compiler infrastructure knows that to this template code corresponds 4 actual implementations. And this is what enables something called multiple dispatch, which means that whenever I will call sum square function on some couple of variables, it will choose the most suitable one for the variables that I pass to it. And if it can't find that, either it will compile one on the fly, or it will complain that there is no method of this function that satisfies the requirements. This is a probably Julia unique feature, at least in higher level languages. And combined with a just-in-time compilation that we have in Julia, this is what it really gives its performance. Because at runtime, it will pick the most suitable method of this function. So a function is a template and a method is the instantiation of the function. And we can pass all the types that we have used so far. This, of course, becomes even more interesting when we pass it composite types. Because, for example, we can come up with a method that implements sum square for 2 points. So in this case, we're telling the compiler how this function will behave when we pass this as a data point. And of course, we're doing kind of the same thing. So summing the squares of both components. And this is our result. So coming from an object-oriented mentality, it's quite a shift because Julia is a function-centric language. So functions take inputs, and it is the functions and methods who are the first-class citizens here, not the data. So compare, for example, to Python, where classes have methods. In this case, functions have parameters. And this is a slight change in mentality, but it's also what allows Julia to be as performant as it is, because all these functions can be compiled just in time or beforehand, and you get very high performance still with a high level type of mentality, so to say. Another feature of Julia is metaprogramming. So Julia represents its own code as a data structure that can be accessed from the language itself. So whenever an instruction is executed, Julia will create an AST, a so-called abstract syntax tree, that contains basically all the instructions that are in a certain snippet of code. But this tree can be manipulated from within the language itself. So it is easier compared to other languages, for example, to transform and generate code from within the language itself. And this is what is referred to as macro. Compared to C and C++, where macros are performed by doing manipulation of the text before the code is compiled, in Julia, the macros are executed when the code has already been parsed and organized in the syntax tree. So you can do a lot more interesting stuff. For example, we have this macro called btime. Macros are usually prefixed or are prefixed with a nat symbol. We can add this btime macro to benchmark a certain instruction. So it will run this function a few times and give the average time that it takes to execute it. And doing this is very trivial in Julia, because we just put btime and whatever instruction, and this instruction will be run a few times, and the code will tell me how long it took to run plus or minus the standard deviation. And there are sorts of things like this we will see now in when we deal with GPU programming that are used all the time to generate kernels for GPU-aware software. But it can be used really for anything. For example, if you're familiar with assertive type of programming, we can have these small tests set a program, and the program can fail gracefully if the assertion is not verified. We can inspect what a macro does by using another macro called macro expand. So if we put this here and put a macro after that, this snippet will return what the macro actually did. So in this case, we're writing assert 1 equal 1. And this is what the compiler would actually do. So if 1 equal 1, do nothing. So all good, go on. Otherwise, throw an exception because we wanted to assert something that turned out not to be true. This is a very easy example. If we do, for example, on the time benchmarking, this becomes quite a lot more involved. So whenever we write this, be time, whatever instruction, the runtime will add all this stuff around it and create, here is an execution.jl, it will create a way to run this benchmark on the fly. So this is very expressive. It allows to generate code automatically in a very straightforward way. And is used in all sorts of places in Julia libraries. I think now we can move to GPU programming. And I will give a couple of interesting examples on things that we can do. So Julia has first-class support for GPU programming through some packages that target GPUs from all major vendors. So we have CUDA.jl, that is the most mature, most likely at this point. We have AMD GPU for ROCm or HIP, one API for Intel GPUs, and Metal for the Apple Silicon GPUs. And up until some time ago, you would have to target each GPU vendor separately using one of these packages. We can also use a package called Kernel abstraction.jl that is very useful to write vendor agnostic code that can just be offloaded onto different GPU vendors, and plus also fall back on CPU if it doesn't find anything. And I will show a couple of examples to do this. So let's do some just preliminary imports. So I will use the plots package to produce some figures with an example that we run, some benchmarking, kernel abstractions to offload on different vendors. This is kind of a pain point for Julia, even though now it's gotten much better. Since the runtime has to compile things the first time they're executed, there is something called a pre-compilation of packages that happens whenever we load a package. So for a long time, the time to first plot, so from running the script to actually seeing something for the first time, was a painful point of Julia. Now it's gotten much better. This in the end ended up being quite quick. Of course, this gets balanced by the fact that any subsequent run is much faster. On the cluster where I'm sitting, they have AMD GPUs. So I will add the AMD GPU package with this using directive. And then I will ask if the AMD GPU package is functional, and it told me true. And this is a node of a supercomputer where there are actually 8 GPUs or 8 compute dies. I will just print information on the first one. So I have this AMD Instinct accelerator with a 64 gigabyte VRAM. As a matter of fact, as a starting point, GPU programming with Julia can be as simple as using a different array type instead of the regular array. So for example, for an GPU, we have the rock array. For CUDA, it would be a Q array. And we can simply instantiate one by feeding it an iterable or any expression that would generate an array. In this case, we're hard coding the numbers. And this will make an array that is already sitting on the GPU. And we're adding one to each of the elements in the array. So this is again an element-wise addition. And then we can fetch it again by reconverting it to a CPU array. Now, in this case, of course, this can be a bit slow. Now it was quite instant, but of course we have this memory copying back and forth that tends to be the bottleneck. And just getting started, whatever operation that we perform on arrays that are sitting on the GPU will be called on the GPU. So we don't necessarily have to use like a more convoluted syntax like kernel launching that you find in lower level languages. In this case, we have a matrix multiplication code. So we have this large matrix that we then move to the accelerator. We use this macro very nicely to benchmark this function. So in this case, we're doing normal, matrix multiplication between these two CPU arrays or normal arrays. And then we will do the same thing on the GPU arrays. Now, the GPU calls are asynchronous because basically we're telling the GPU, is your data, run it, but then the control of the script comes back to the host. So if I just time this, it will give me an unreasonably slow number because as soon as the computation is launched, then according to the runtime, it's over. So to actually be able to benchmark the time that it takes, we have to synchronize back to the device. So we're telling our CPU, look, wait for the GPU, and then you'll know that it's over. So now we can run this. And this function is being run, I don't know exactly how many times, but just to have a large enough sample size to estimate the time that it takes to run more accurately. So on the CPU, it took 536 microseconds, and on the GPU, it took 69 microseconds. So we already have around a 10 times speed up. And this is even including the time that it took. Well, no, actually, in this case, we're not copying it back, but yeah, we get the speed up. Usually, GPU vendors have optimized library to perform matrix operations. For example, probably some of you are familiar with the BLAS or LAPACK instructions. NVIDIA has their library called QBLAS, and AMD has an equivalent called ROCBLAS. The AMD GPU package in Julia is clever enough to offload these operations to the appropriate library that does this. So when we're calling this matrix multiplication, actually the runtime is calling the BLAS version of that is being optimized by AMD to perform as quickly as possible. If we were using CUDA, it would have been the same. The CUDA.jl package would dispatch it to the BLAS implementation of that. So this means that in many cases, you don't have to implement your own primitives. Many of the important kernels like matrix multiplication or linear combinations, even FFTs and a lot of stuff was already implemented by the vendors. And whenever it's used, it's dispatched automatically there. So this is nice. And we get our nice speedups that we're after. but so far it's still vendor specific. What we would like to do in an ideal world is to have a code that is written once and runs everywhere. And this is where the kernel abstraction package comes into play. In this example, we want to sum two arrays A and B and store the result in C. And I will walk you through the code in a second. But this is what we will achieve. So we have a function, and this will run seamlessly on the CPU or GPU. So the function is called vadd. It is common practice in Julia to add an exclamation mark when a function modifies one of its parameters. So in this case, we're giving it the C and we're modifying it because each element in C is the sum of A and B. So this is just common practice in Julia to have exclamation mark. So we give it the kernel macro. This basically tells the runtime that this is a function can be dispatched on some accelerator or on the CPU. And what we want to do is, as I said, sum element-wise the two arrays and store the result in C. So we take the index I, and this global index global syntax tells us that this index I basically spans all over the size of the array C, right? By extension A and B. Why is this important? It's important because, as I showed you before, threads on cores on GPUs are grouped in these streaming multiprocessors. And this means that if we have a very large array, it will not fit in one streaming multiprocessor or in a block. So normally, if you ever seen CUDA code before, for example, to obtain the index, you will have to do something very complicated like this. So the size of a block times, the index of a block times the dimension plus the thread number. Julia kind of simplifies all this for us by just saying, look, this macro gives you the global index across all the computation. And then what we do is what we set out to do. So each element in I is, each element in C is the sum of the corresponding elements in A and B. And inbounds is a way to speed up the performance by telling the runtime to not check if we're going outside of the size of the array. And we're allowed to do that because we're using this index that the runtime already told us that will be inbounds. The only thing that is missing is this const macro. This is interesting because since GPU kernels are asynchronous, it could be that while we're reading A, there is an element in A, there is a thread that is trying to write on it. Or that between different executions, the A and B have changed. This can be because the A has been overwritten somehow, or because some memory has been aliased, because, for example, some other part of the process is trying to write there. The const is us ensuring to the compiler that A and B are not going to be changed. And this allowed for a faster read. And if you're ever seeing CUDA-C, this is kind of like using the restrict CUDA-C keyword. So we can add this to tell the compiler, look, we're not going to change A or B and no one else is. So don't bother put some kind of sanity checks there. So this is the kernel. And then what I did was just to write a small wrapper function around it that will get the backend of this, which in this case means that I want to sum A and B and put it in C. This could be CUDA arrays. This could be AMD GPUs array, could be Intel, could be CPU. So I'm asking where this array is sitting. And I'm compiling a specialized version of the vadd function that runs on the backend. So if this is a normal array, this will become a normal, CPU adding code. If this is a AMD GPU array, like we will do soon, this will become instead will be compiled on GPU. So I get the right version of the kernel that I want to use, and I just launch it. And what I pass to it is the 3 parameters that it needs, plus the total number of work items, so the total size of the array, that is C. So I can run this now, and I have a generic function with one method. Now, the nice part here is that I have a normal CPU array. This is a vector of size 10 filled with 3s, and this is a vector size 10 filled with 2s. And I will just launch my function, and I get a 10-element floating vector filled with 5s. Now, I just create my arrays on the GPU instead of the CPU, but I don't change anything else. I call the function with exactly the same syntax, and now it will take a bit longer because you have to compile this function for the first time, but I get in return a 10-element rock array, so a memory is sitting on the GPU, and I didn't have to change anything in the code. So I get literally the same function that runs on a CPU or a GPU. And I just have to call it with the right type of data. And this makes it quite interesting for developer productivity. I will show also another slightly more complicated example, because in this case, each element was independent. So all these sums, this is an embarrassingly parallel for loop. So each element is independent. But a lot of times we need to communicate with a list the closest points to us. And I will show you how to do it. So I'm bringing in something from my own background. That is the heat equation. That is, yes, this form, and is used to describe diffusion processes. So this kind of horse hoof is a high temperature region, and heat will flow from the hot to the cold part in a gradient smearing process. And this is described by this equation, where the evolution in time of the temperature is proportional to the Laplacian. It's not really important, the physics. What is interesting is that we want to try to solve this equation on a rectangular 2D grid like this. And the heat equation can be approximated or can be solved numerically using these 2 formulae. So we have the superscript that indicates the time step, so where we are in time, and the I and j that instead describe the position in space along this grid. And when we compute the temperature in each point in a subsequent time step, we need a so-called 5-point stencil. So to approximate this derivative, we need the point that we're interested in, the point just above, left, right, and down. So each thread has to have access to the 4 points around it, plus itself, of course. And this can be solved quite performantly on GPUs because there's not a lot of communication involved. All these processes are quite local. We just need, very close variables, at least for a 5-point stencil. There are more complicated schemes where you need points further, but the more local it is, the better for the GPU. So what I will do is just do some boilerplate code So I have the size of my regular 2D grid, where each cell has a size of 0.1 and the number of cells is 128. And for numerical reasons, I can only advance in time by a certain amount that is given by the grid size. What I will have in this case is a temperature that is constant everywhere and is 50 degrees. And then in the middle, I will put a circle in which the temperature is 200. So I have this hot disk. And I will just run this now. And so I create my temperature field and I initialize it to all 50 degrees. And then I just make a simple computation to isolate the cells where the temperature is higher and be sure to set it to the temperature of the disk. Since we have time marching, we need at each instant the tn+1 we're computing, but also the old one. So I will initialize it to at the first step being the same. So now, apart from the numerics, the real workhorse is the diffusion kernel. So it is the function that will actually compute the updated value of t. And this case is quite interesting because I will have a 2D grid. So I can make very simply two indices, I and j. In this case, it's still the global index, but instead of being a single number it was before, is a tuple. So it's a couple of numbers that describe the horizontal and the vertical direction. Then what I do is just to, loop over I and j, compute these derivatives that I have shown you up here. So the derivative with respect to x and the derivative with respect to y. It's here. And then I update the temperature field according to the formula that I've shown you above. Why do I have these ifs here? That is because if I loop all over the domain and I'm asking for the values at I+1 and j+1, at some point I will violate the domain, because if I compute at this point, there is no I+1 after this. So what I did was to create some ghost points. So when I initialized my domain, I made them of size n+2 and n+2, so that I never touch those cells, and those become my boundary conditions that I never touch. So I just loop over I and j without getting to the very end. I compute t. Then here I'm doing basically the same trick as I did before, to use the same code both on the CPU and the GPU. So we'll just get the right backend and run it. And now we can just run this on the CPU. So at first I showed the initial condition. So I have a temperature of 200 degrees here in the circle and 50 everywhere else. Then what I do is that for each one of my time steps, I evolve the field. So I compute the diffusion kernel. And then I need to carry with me the previous time step, because I will, I will need to carry with me this time step because I will need it later to compute the second one. So I just make it so that the previous time step now will point to the first one. It's basically just a way of having both the current and the old state with me. So this is the initial condition. And this is after 500 time steps. So we can see that our bubble of hot fluid has been diffusing. And this took 0.02 seconds to run on the CPU. Now I can do the same thing on the GPU. So I will recreate again my initial condition T. And then I just turn it into a rock array. And then what I do here is just exactly the same. So I evolve this on the GPU arrays instead of the CPU arrays, and I display also those ones. So without changing anything to the code, rather than just these 2 lines, I got the same thing on GPU with a speed up of around 12 times compared to the one before. So I got the same result, but 7 milliseconds instead of 5 centiseconds, I think. And this is just all by means of using this kernel abstraction package. So this will run indifferently on the CPU or GPU, and just some checking for binary conditions. But apart from that, it doesn't make a difference in the way that I wrote the code. So, yep, same thing. We got a 12% speed up without any fine tuning, but we can actually do a lot better, because for each one of the ij points, we're reading 5 values, right? We have the 4 around it plus the 1 in the middle. And we can do some clever caching, for example, with the local memory of each streaming multiprocessor to avoid reading from the global memory several times. And if you're interested, we will share this notebook and I will include an example where I do that. And this allows us to not read 5 times from the global memory per time step per node. And we can do a lot of fine tuning, but that will run indifferently on CPU or GPU. But the way that it is, even with a very naive implementation and without any rewriting of the code whatsoever, we got quite a good speed up. So this is, I think, what I had regarding, more like scientific computing type of application. Julia is possibly not as well known for data science, but there is actually a lot of work done also in that area. So for example, the MLJ package is like a repository of many different models, common machine learning algorithms, like clustering things and regression models and all sorts of things. And Flux, for example, is a very powerful package for deep learning. I had an example on how to do, for example, classification with neural networks, but for the sake of time, maybe I can skip it. But this can also seamlessly scale to GPUs without basically almost any touch to the code, kind of like in examples that I showed you. And yeah, I think this was it from my point. Are there any questions?